each access point may serve as a base station for multi-cell system, and we need to coordinate the operation of such a hybrid access point. So in this talk, I will describe how to optimize such operation in actual multi-cell scenario. So in the multi-cell scenario, inevitably there will be an interference especially from the wet process, because it is a TDD process. But as I will describe in more detail in the following slides, but interference may be beneficial to certain cases, which is quite different from the traditional communication system. Because in the traditional system, interference results in the lower performance normally. So in order to obtain a possible solution for the issue of interference, we can consider several things. For example, like scheduling or beamforming or cognitive radio, as well as cell operation. So there are many possible techniques to solve those issues. So actually, there are several works in this area, but most of the work has been done relatively recently, like 2 years ago. So some interference there was a work based on sweep applying in the interference channel, and recently there was some work on the coordinate multiple comp system combined with the power and wireless power transfer system, and also there has been work on the cognitive radio. But none of them has been properly addressed general multi-cell scenario. So this is the system model that I'm going to talk in today's speech. So I will consider the WPCN in two-user channel. In this case, there is two separate WPCN. The cell 1 supports user 1, and the cell 2 supports the user 2. But in the WPCN, in the first downlink phase, hybrid access point sends the RF signal to charge the user 1, and in the subsequent uplink system, user 1 transmits the data back to hybrid access point. During this process, we have interference. For example, in the downlink side, hybrid access point, the signal coming from the hybrid access point 1 may reach the user 1. So as I mentioned before, in the traditional communication system, such undesired signal has been regarded as interference, which needs to be canceled or mitigated properly. However, in the wireless power system, the situation is different, because the signal coming from the base station from the other cell, the signal coming from the other cell may be utilized to harvest energy as well. So this path is no longer interference. So this is creates a new situation in wireless power system. So here our objective is how to maximize the throughput in this two-cell scenario. So I'm going to talk about the system model. Actually, I need to wet, second one is wet. So in the downing, the energy is harvested at the mobile device, and the uplink based on the harvested energy, the energy is transmitted back. But because cell 1 and cell 2 may operate independently, they may have a different time slot. The first cell has a tau 1, whereas the second cell may have a tau 2, which is different from cell 1. So it'll gives rise to an interesting situation where, for example, in the middle, there will be some misalignment between the neighboring cells in the TDD operation. So this can be divided into three different regions. First region is both cells operate in the wet process. In the second stage, cell 1 operates in the downing wet, whereas the cell 2 operates in the wet. That's the second step. The last, third operation is when the cell 1 and cell 2 both operate in the uplink wet. So we divide into three different categories. So this is the first category where both systems operate in the wet operations. So as I mentioned before, the signal from the first cell base station may reach the user in the other cell, and this signal can be utilized to increase the harvest energy of the user. So in this case, the amount of harvest energy can be described as follows. And in the second stage, there is some misalignment difference between the wet and wet in cell 1 and cell 2 that is described in this scenario. In the first cell, still user one is charging its battery, while in the cell 2, user 2 is transmitting the data back to its corresponding base station. So in this case, there will be some interference between two base stations, and also user 2 may interfere with the first user. But as I mentioned before, this signal is not an interference to user 1. On the contrary, this signal can be utilized again to harvest energy for user 1. So the whole formulation may be different from the conventional traditional communication system. Lastly, this plot shows the final stage where both cell 1 and cell 2 operate in the wet procedure. So in this case, user 1 and user 2 both transmit the data back to base stations. In this case, this is same as the conventional MAC processing the communication system, and because this transmits the signal conveying its own data, this crosspath will act as an interference signal, and the corresponding receive signal and the keyboard rate is shown here. So now I will show you the results, how to allocate the power and time. So this is a mathematical formulation how to maximize the performance. So major goal of this system is how to maximize the throughput of the system by optimizing the time allocation tau and its allocated power for each user. So based on the several constraints, this constraint mainly comes from the fact that each sensor node can transmit the energy only when the harvest energy is sufficient to transmit certain amount of power. So those constraints come from those facts. So I'm not going to go into detail how to solve this problem. And actually solving this problem is non-trivial, and it needs a lot of techniques to solve this non-convex problem. Just to summarize the overall algorithm, it is difficult to jointly optimize the time and power, but in order to obtain a local optimum solution, we apply the alternating approach. First, we update tau based on a given p, and after that, we update the power based on tau, and we repeat this process. And then we can show that those iterative process will generate the local optimum solution. So this is a little more detailed approach. So maybe a little too heavy to talk describing today's linear talk, but I'll show you some results skipping the derivation. So we can solve the original problem by converting to the weighted MMSC approach. And this is the one. After converting the original problem, the original problem is transformed into a convex problem. And convex problem is much easier to handle. So this problem can be used by applying a well-known Lagrange dual method. And then also similarly, time allocation can be solved based on this summary maximization problem. Also, this is a concave problem and easy to solve. So the major technique applied to solve this one is how to transform the original non-convex problem into the subset of convex problem, so that we can apply the well-known convex tool. So this is a summary of the overall algorithm. First, we initialize the tau, and then for given tau, we optimize the power location. After power location is done, we update the time allocation tau based on the power computed from the previous stage, and then we go back. So compute the power and the power and tau subsequently. So we alternating repeating this approach until converges. Actually, the simulation shows that it converges quite fast. So as a special case, we can consider a system where if the two cells has the same boundary. So in this case, we can derive the closed form solution. The closed form solution is actually shown here. In this special case, the optimal solution can be derived in this one-line expression. So we can prove that actually it has a unique solution. And to compare with the other conventional system, you can consider the other TDMA system, where the cell 1 and cell 2 separate the weak process in the TDMA fashion. TDMA situation can be solved by applying a similar technique. I will skip the TDMA derivation, and because of the time limitation, I'll explain the simulation results. Maybe there's a little bit equations are broken, but I divided into two different cases: so strong interference case and the weak interference case. To sum up, we can see that first the blue curve shows our proposed speed, whereas this green curve shows the special case of each cell, both cells have the same tau. So we can see that optimizing tau is quite critical to improve the performance. So by allowing different tau for each two different cells, we can achieve a lot of gain compared to the single tau system. And we may have a different result, but still we have a good performance gain in both cases. And this is another average summary performance gain with respect to SNR. So we can see that actually this red curve shows that if two cells operate completely independently without any operation, so each cell optimize the performance based on its own channel without considering the other cell operation. Compared to this, by taking into account the other cell's operation, we have a substantial gain. So it is a good example of how the applying communication theory is quite important in optimizing the wireless power transfer system. So it's a cooperation between cells is quite important. The similar approach, similar conclusion can be made in the other case. But in this case, actually, no interference. Independent cell scenario has a small gain because it has the simulation environment has a very weak interference. So in this case, we may have the gain may be reduced. And this is another example of the TDMA reference system, and it shows a good performance gain. So I'll give you the summary for this talk, and I have briefly introduced the method of wireless power transfer technique, which has gained a lot of interest in the market. So maybe it's a little different, maybe far away technique to be implemented in the near future, but I imagine that this kind of technique can be implemented in maybe a 6G system. Who knows? But imagine the new system where whenever you get into a building, then you don't have to worry about the remaining battery because your device, mobile phone, will be automatically charged without worrying about the battery. That will be quite convenient. So I think it will have a lot of impact in the future communication system overall. So this is a relatively new topic in this area, so I think it deserves a lot of attention, a lot of interest. So I'll take this opportunity to introduce this interesting topic. Okay? And this is a reference for my talk. Thank you.
Let's thank the speaker. very exciting talk. I'm sure that there will be lots of questions, but we have some time limitation. We would like to give him a certificate of appreciation. So maybe you guys can ask one or two short questions, then will be very great. Please ask a short question.
Can I use any microphone?
Is there a microphone?
Okay. My name is Yoo Hoon from Korea. Very interesting topics. Sometimes I feel very optimistic in this area, in these topics, because a lot of papers can be published, and we have many chances to study and investigate to publish the paper. But I feel some point of view, I feel very pessimistic. Even in these data, the seller point is now power consumption. I read one paper and published in one papers about that. Simply, PSK is better than FSK. It is very simple modulation technology. But we have to consider one more, the RF stages or other circuit system. When compare everything, FSK is better than PSK. Therefore, in the medical implementation system design, the FSK is used for that. In that point of view, how do you like, how do you expect it, the efficiency of the power by this power system? That's very important for the long distance survey.
Thanks for your insightful comment. Actually, as I mentioned earlier, one of the major limitation or major bottleneck of this in this area is that how to improve the efficiency. So as Professor you mentioned that current technology has a very low efficiency compared to other conventional techniques like a resonance method. So I'm not the expert in the RF circuit design, but maybe some of the audience have a much better knowledge than myself. But actually the colleagues in our school are working hard to improve the power efficiency, and they have been reporting much better progress in terms of the better efficiency. So actually, most of the work from the communication point of view, I did derive some formulation, assuming that overall efficiency has reached acceptable performance, but those issues should be addressed by some RF engineers, and I hope that because I've been observing some good progress in the past, so I think the near future the efficiency will improve to satisfy some required performance measure.
Yeah, thank you very much. Since we have time very limited, I would like to now proceed to the ceremony of appreciation by general chairs. Please, the general chairs, come forward to the podium and be prepared to give him the certificate of appreciation.
There are photographers who's going to take the pictures.
Thank you, Professor Lee, for accepting our invitation to come to Okinawa and for your nice talk that give us another stronger resilience. Thank you very much.
Thank you very much. Let's thank the